This is Note-Taking Guide 5.1 for Systems of Equations, Math 3. Today we're going to solve a system of equations by graphing and see if we can't find the solutions in various ways. The first example here is it says a solution is a value or set of values that make an equation true. For example, y equals 2x. If we put 2 in for x, then y would be 4 because 2 times 2 would be 4. We've found solutions for equations that way all of the time, and then the graph of that equation, y equals 2x, is a visual representation of all of those ordered pairs that would satisfy that equation. So today what we're going to do is we're going to look at some that would be a little bit harder to do by substituting values in. So for instance, say we want to find a solution to these two equations together. Well, if I put 0 in for x, I would get 0 out for y. But does it also work in the second equation? If I put 0 in here, I'd have 0 plus 2, and I'd get the square root of 2. It did not satisfy both equations, so it's a little bit harder to find the numbers that will satisfy both equations. So what we do is we graph them instead and find the points of intersection. So here they are over here. We're going to graph them and find points of intersection. We know that this graph right here is the absolute value graph. It has no left or right movement and no up or down movement because there's nothing added or subtracted there. So we start at 0, 0, and then we follow the pattern of an absolute value graph, which is over 1, up 1 in both directions. So I'm coming over 1 and up 1 in both directions for my V-shaped absolute value graph. Then what I'm going to do is graph this other equation. This equation here is a square root graph, which means it's kind of a parabola laying on its side. So the plus 2 tells me to move left 2, and then I follow my pattern. Up 1 over 1, up 1 over 3, up 1 over 5. And my graph goes through those ordered pairs. Now look and see how easily that is to see where my points of intersection are. There's only 2 spots on this graph, or 2 ordered pairs, that would satisfy both of those equations. The first ordered pair would be negative 1, 1, that ordered pair right there. And my second ordered pair would be 2, 2. So I could substitute those into both equations and both would be correct solutions. Okay? Sometimes we might have to estimate the solutions because algebraically might be a little difficult to do, and we might have to actually just guess where we think that is. Maybe this is 8.8 and 3.2 or something like that. Your guess might be different than your neighbor's. So sometimes it's better to solve with algebra instead of solving with graphing. So why would we want to do this? Well, the first thing we'd want to do is figure out why systems are important. Lots of times we use systems of equation for profit and loss when we're working in a business, or a break-even point when we're working in a business, or cost and revenue graphs. So here's some examples of when and why we would use that. So when we use graphing to solve an equation, we have different kinds of answers that can happen. The first thing that could happen is the graphs don't intersect at all. When that happens, that would be no solution. In math, we represent no solution with the empty set. Over here on this graph, these intersect in one solution, one exact solution. We would give that solution as an ordered pair, an x comma y value. There can be more than one solution. These graphs look like they intersect at least 4 times there, so we could have 4 solutions there. We would have 4 ordered pairs that we would draw out as our solution. And then sometimes when we graph 2 systems or 2 equations in a system, you might graph the first equation, and when you graph the second equation, get the exact same solution. That would be when we have infinitely many solutions. Lots of times we choose to write that as all real numbers, a capital uppercase R. So what we're going to do now is we're going to graph these and see what happens. So 2 equations here on the same graph. The first one here is a line. It's in slope y intercept form. Y is equal to 2x minus 5. So I go down to -5, I go up 2/(n)/1 for my slope of my line. Now when I'm graphing for a point of intersection, I try to do more than one set of points so that I don't get confused as to where I'm going. This is a square root graph, right one and up one. So right one, up one. And then my pattern gets times by a -2. So instead of going up 1/1, up 1/3, I'm going to go down 2/1, down 2/3 for my graph. And I can easily find my point of intersection here. That's going to be at 2, -1. Sometimes when we're solving an equation, it's going to look like this. And we decided last chapter even that we could take these two equations and we could set them equal to each other and solve them, or we could just graph each side separately. So right here we have these graphed separately or written out as equations separately, so we can graph them separately. The first equation is a cubed root graph, so that's kind of like that snake laying on its side graph. I'm moving right 3 and up 4, right 3, up 4. And then we're just going to kind of go over 1, up 1, and over 1, down 1, and my snake graph is going to go through those ordered pairs. This other one is a line that starts up at 7 and goes up 3 and over 1, which is kind of off the graph. So let's also go down 3 and over 1, down 3 and over 1. And draw your graph through those ordered pairs. So when we're looking at that point of intersection there, we're looking like, oh, I can see what I did wrong. Oops, that was bad of me. You guys, I shouldn't have started up at 7. I should have started down at 7. So I start down at 7 and go up 3 and over 1, up 3 and over 1, up 3 and over 1, up 3 and over 1. That looks like a nicer point to have a point of intersection at. That would be the point 4, 5. So again, I started wrong on this graph. Sorry about that. I should have started at -7 because of the minus, not at +7 with the plus. Alright, this set of equations here are set equal to each other. We're going to graph the first one by itself. Then we'll graph the second one on the same graph and see if we can find a point of intersection. This is a parabola that goes right 3 and up 7. So right 3, up 7. Instead of following the pattern over 1, up 1, over 1, up 3, I'm going to take my pattern upside down because of the minus. So over 1, down 1, over 1, down 3. And then I would go over 1, down 5 because of my pattern. This other graph right here is a square root graph. So this one laying on its side with its domain error being taken care of with only half of it showing. So right 1, up 9. And then instead of up 1, over 1, up 1, over 3, I'm going to go down 3 over 1, down 3 over 3, down 3 over 5. And my graph's coming through just like this. For two nice points of intersection there at 2, 6 and at 5, 3. So sometimes they want us to be able to compare the things that are not in the similar form. So this is a graph, this is a table, and we still want to see if we can find a point of intersection. So what I would suggest to do is let's just graph these on here and see if we can find a point of intersection. We're going to be at -6, 8, -4, 7, 0, 5, 4, 3, and 6, 2. And when you draw your line through those ordered pairs, it's really quite simple to see that point of intersection. You're at 2, 4. One last example doing that same exact thing. This time we have to graph both of them. So let's do -3, -2, -2, -3, -1, -2, and 0, 1. I can actually tell that this is going to be a parabola. I'm just going to add that extra point over there and graph it just like this. And then I'm going to graph this. This is the absolute value graph that goes left 2 and up 3. And then my pattern would have been over 1, up 1, but because of the minus sign, I'm going to go over 1, down 1. And I can see my points of intersection already on that. I'm at 0, 1, and negative 4, 1. So again, what we're doing here is we're graphing more than one graph on the same coordinate plane and finding their points of intersection. Good luck with your assignment, you guys.